It's sometimes convenient to find the expected value of some function of our random variable. If g of x is some function of a discrete random variable x with probability mass function p of x, the expected value of g of x is, well, not surprisingly, it's g of x times p of x. Again, you can think about this as the sum of the products of the payoffs with the probabilities. While we could, and sometimes must, calculate this from the formula, in some cases we can compute it more easily. To avoid having to deal with the indexing, we'll use the notation, with the implication that the sum is going to be over all elements of the sample space. First, let's consider some properties. Suppose g of x is c some constant. Then the expected value of c is going to be c times the probability of x. But since c is a constant, we can remove that factor outside of the summation. And this is the summation of our probabilities over all possibilities. So that summation is just going to be 1. And so this gives us our first useful result. If c is a constant, the expected value of c is just c. Next, suppose g of x is the sum of two functions. Then our expected value of that sum will be, which we can rearrange. And since, for now, we're dealing with finite sums, we can split it and rewrite. And note that this first summation is just the expected value of f of x, and the second one is just the expected value of h of x. And so that gives us our second useful result. The expected value of a sum is the sum of the expected values. Finally, suppose our function is some multiple of some other function. Then the expected value of g of x will be, and again, since c is a constant, we can remove that factor outside of the summation, and here we have just the expected value of f of x. And consequently, the expected value of a multiple of a function is a multiple of the expected value. And by our theorems, we can say that the expected value of a linear combination of two functions is the linear combination of the expected values. And so if it means anything to you, we could say that E is a linear operator. If that phrase doesn't mean anything to you, it really is a fancy way of saying that the above statement is always going to be true. Consequently, given some value of the expected value of x, we can find others. So, for example, suppose x is a random variable where the expected value of x is 15. Let's find the expected value of 3x plus 7. So we find the expected value of, well, that's a sum, so we can split it. That's a constant multiplier, so we can move the factor outside. We know the expected value of x is 15. The expected value of a constant is just the constant, and so our expected value will be, or maybe we have the expected value of x squared and of x. Let's find the expected value of x minus 5, quantity squared. So we can expand inside the expectation to get. Now, for reasons that'll be made clear a little bit later, it's best to get into the habit of writing the subtraction as adding a negative. So this sum is x squared plus negative 10x plus 25. And since this is a sum, the expected value of a sum is the sum of the expected values. The middle term has a constant multiplier of negative 10, so we can move that factor outside to get, and we can fill in our values for the expected value of x squared, and the expected value of x, and the expected value of a constant. So this introduces an important idea. We will sometimes want to know the expected value of x squared. So let's consider the following problem. Let x be the number shown when a fair six-sided die is rolled. Does the expected value of x squared equal the square of the expected value? So we can compute the expected value of x. That's the value times the probability, which will be Meanwhile, the expected value of x squared, well, that'll be x squared times the probabilities, which will be and now let's compare them. The square of our expected value to the expected value of our square, and they're not equal. And so the expected value of x squared is not in general going to be equal to the square of the expected value. Since there's no obvious relationship between e of x squared and e of x, these expected values are particularly important. And math ever generalizes, so we introduce the following definition. The nth moment about the origin is the expected value of x to the n. We'll take a look and see why these are important later.